So let's look at our second exam question in the elastic collisions in 2 dimensions topic. Okay, so in this case, we're still looking at uniform spheres hitting each other, but this time with a little bit more consideration on the energy that's taking place and sort of trying to work out the speed in terms of some unknown parameter. In this case, the unknown parameter is the ratio of the two masses. So you're given the first smaller mass is mass m, and the mass on the right hand side, by convention on the right hand side, we'll say is km. So take a look at this question if you can. It's got 3 separate parts. Again, just attempt them separately first. If you get stuck, feel free to take a look at the work solution. Pause the video now. Okay, so as usually is the case, you want to draw your before and after diagram of the collision and label, either vectors or scalars appropriately. So let's do that first. Okay, so I've drawn us the sort of before and after. If we look in the case of before, we know that A is moving at 60 degrees and with a speed of u, and B was stationary? Yeah, B was stationary. It's going at 0 meters per second. And in the after case, we don't really know what happens. They're going off in some sort of direction. However, let's just focus on the sort of key components. So we at least know for B that, same logic, if you did the exam question 1, same logic that we know it'll be going completely horizontally. So again, let's give it a scalar w to represent that speed, and we know it's horizontal. And in the case of A, don't particularly know, what's happening in terms of, the vertical at this stage, but let's just focus on the horizontal. So let's say the how can I best sort of mark this? Let's say the horizontal speed here after they've collided is, I'm going to call that v, and then the vertical, I'm just going to say for now just question mark. I don't particularly care. Okay, so let's just focus on the horizontal situation. So in the horizontal situation, let's consider center of mass horizontally. We've got u cos of 60 times mass m, and adding that to, well, in this case 0, and then that's going to be equal to, and now we can just use v directly because we're looking at horizontal, mv plus mkw, and cos 60 is in fact a half, so that's just a half, and let's already cancel out the m's, so we'll get half u equals v plus kw. Okay, and then let's also think about coefficient of restitution. So E is going to be equal to separation over approach. So the separation here is nice and easy now. It's w minus v. So I've done the right minus the left horizontally, and therefore I'll divide by the left minus the right. That is to say, the left horizontal speed, the object on the left, which is A. What is its horizontal speed? It's u cos 60 minus the horizontal speed of the right object, which is 0. So that's w minus v all over u cos 60. Cos 60 we know is a half, so that's equal to w minus v all over a half u. And since we've been told E is equal to a half, that implies that a quarter u is equal to w minus v. And that should be it then, shouldn't it? W minus v equals a quarter u. couple that equation with this one. And what are we trying to do again? We want to find the speed of B immediately after the collision. So we're going to look for W and make that the subject, and hopefully cancel out, because there's a U here and a K there, we're going to cancel out this V. Okay, so that should work. So let's try that then. Let me just take the key two equations that we've come up with. Okay, and we want to make W the subject while cancelling out the V. In which case, the easiest thing actually is probably just add the two equations together, because then the V's cancel out quite easily. A half plus a quarter, that's 3/4. And that's equal to, and then I'll do V plus minus V cancels, KW plus W gives me this, which is just 1 plus K times W. And that implies that W is equal to 3U all over 4 times K plus 1. Okay, and we've answered part A. Okay, so now looking at part B, I've kept the diagram and I've just kept these two equations because I think we're going to have to make use of those as well. And let's read the question first actually. So it's saying after the collision, the direction of motion of A, so we're looking here at A, makes an angle arctan 2√3. So, you know, in some sense or another, we've been given the angle that it's going to move at, specifically the ratio between this vertical and this horizontal component of the speed. Now actually, I put a question mark here earlier because I didn't really care what this was, but really we know what this is because this vertical component of the speed is perpendicular to the line of centres, which means it's just going to be the same as what it was before. So the original vertical speed of A would have been U times sine of 60. So that's √3/2U. And that's not going to change just because it's collided. So let's write that in now actually. So that's √3/2U. Okay, which is exactly the same as it was originally vertically here. That's the U sine 60. So we've got that there. Okay, and then we're told this angle 2 times √3. So the arctan being 2/√3, what does that tell us then? So the tan of the angle is 2√3. And remember, that's the tan of, effectively, if we're looking at these two blue components, it's saying, okay, I've got V, and I've also got √3/2U, and it's saying that this angle is such that this is the case. So, seeing as tan is opposite over adjacent, that tells us that √3/2U is going to be over V equal to 2√3. And we can probably just make that a little bit neater. So I'm just going to rewrite that over here as √3/2 times U equals 2 times √3 times V. Yeah, and actually let's just multiply both sides by √3. So if I multiply both sides by √3, I'll just end up getting rid of these √3s entirely. In fact, no, what am I even talking about? That's overcomplicating it. Let's just get rid of √3s entirely. So we'll end up with a half equals 2V, or in other words, U equals 4V. Yeah, that's much simpler. Okay, so U equals 4V. Let's stick that down. Okay, so now let's make use of the equations we've got here. We're eventually trying to find out what K is, so we're certainly going to need to use this first equation with the K in it. If U is 4V, let's actually substitute that straight into there. So that's going to give us 2V equals V plus KW, which implies that K, so I'm just jumping around in my head a little bit for a moment. So V equals KW, so therefore K equals V over W. Okay. And then W, if we remember from the previous question, we found out what that was, didn't we? Hang on, let me just check if I've done this correctly. I think I have, but not in a direction that's helpful actually. So let's change this. Let's change which way we substitute this actually. You'll see why in a moment. It makes more sense to do it this way around. Instead of cancelling out the u, let's cancel out the v. So still using this equation. So if u equals 4v, therefore v equals a quarter u. So that's going to be a half u equals a quarter u plus kw, and therefore kw is equal to a half u minus a quarter u equals quarter u, and that implies that k is equal to a quarter u over w. Okay, and now we'll see why I did it that way around instead, because in the previous question, if we take a look, we've already got w, and not only that, we got it in terms of u, which is going to be very helpful. So let me take that across to, so we're using part A now to help us with this. If I substitute that w into here, we can now see these u's are going to cancel out, aren't they? So in fact, if we clear a bit of space, let's proceed with this equation having substituted in this w. So I've got k equals a quarter times u all over w, which is 3u over 4 k plus 1. So instead of doing all over, let's actually just multiply by the reciprocal. So we've got u times 4k plus 1 all over 3u. Great, because now that u and that u cancel. And, oh, in fact, that quarter and that 4 cancel. So that tells us that k is equal to k plus 1 all over 3, which implies 3k equals k plus 1. Okay, and then we're getting there, 2k equals 1, and that implies k is equal to 1 over 2, which is exactly what we needed to show. Okay, so then on to the final part. We're looking at loss of kinetic energy. Now, it should be clear that this is going to depend on what the initial speed was in the first place, right? Because this is it's just a number, effectively, the loss of kinetic energy. But we've still never been told what u is, and we haven't been given enough information to figure out what u is. So our final answer is going to be in terms of u. What we should now do is make use of this k equals a half, and substitute that into whatever other things we've already found out. So for example, w equals that was our part A. If we substitute a half into there, so you're going to get 3u all over 4 times 1.5. Put that in your calculator, or better yet, just do it in your head. That will be a half u. Okay, and then we've also got here, this was also used at some point in part B, we worked that out. That tells us V equals a quarter U. Okay, perfect. So now we know all the things that are going on with this scenario before and after. So this V, which I'm erasing, and this W, which I'm erasing, I can now replace those accordingly with a quarter U and a half U. Okay, so everything's in terms of U's now, the before and after. We shouldn't really need this anymore now. I'll delete it for now. And let's just do our before and after table for the kinetic energy. Okay, so I'm going to consider A and B, before and after. What is the kinetic energy? The B before is easy, that's 0. The A before is easy, a half times m times u squared. Then the after for A, what we can do, which hopefully seems obvious and, but perhaps you haven't made that much use of, is the fact that we don't need to combine these two components and then, get effectively the hypotenuse and then turn that into kinetic energy. We can just find the kinetic energy of the components separately. That's completely legit to do. So let's just do that. A half times m of the first component, the horizontal, squared, plus a half times m of the other component, root 3 over 2 u squared. So that's basically 3 over 4 times u squared. And then for b, we've got a half times km, and k was a half, so there's a half times m times the speed, which is a half u all squared. Let me just have a think about that. Yeah, I think that does make sense. There's a lot of halves in there, but that does make sense. Okay, and then the loss is going to just be the before minus the after. So we've got a half m u squared minus. In fact, let me just, so I can save a little bit on writing out. Let's just put a half m as a factor outside everything, because I know that's a factor in everything. So we've got a half m times u squared, and then minus, so a quarter u squared, that's a 16th u squared, minus 3/4 u squared, minus, and then we've got a half times a half m, but the half m we're taking out, so one of those halves we take, times the half u squared, that's a quarter u squared, times the one of the halves we took, that's an 1/8 u squared. Okay, so then we're effectively working out what is 1 minus a 16th minus 3/4 minus an 1/8. And you can either work that out or use your calculator or however. We should end up with 1 over 16 u squared. And that then gives us a final answer of 1 over 32 times m times u squared. And that is in fact the right answer. So let's look at our second exam question in the elastic collisions in 2 dimensions topic. Okay, so in this case, we're still looking at uniform spheres hitting each other, but this time with a little bit more consideration on the energy that's taking place and sort of trying to work out the speed in terms of some unknown parameter. In this case, the unknown parameter is the ratio of the two masses. So you're given the first smaller mass is mass m, and the mass on the right hand side, by convention on the right hand side, we'll say is km. So take a look at this question if you can. It's got 3 separate parts. Again, just attempt them separately first. If you get stuck, feel free to take a look at the work solution. Pause the video now.